This one is pretty easy quiz, right? Everybody should get those questions. All right, let's give 1 minute and we start class. So for today's class, it's going to be more conceptual explanation to wrap up what we have talked about, like this particular chi parameter. How do we understand it? And what is existing theory to explain what's a chi and what's the limitation for the current theory. Okay? Then we're going to have a recapture of this whole chapter, because as I mentioned, this will be the last lecture for the chapter 7. Then we're going to have a review of homework coming up next Tuesday. I will be traveling out of the country, so I will pre-record it. If you have a question, please email me. That's the way I can handle that. So on Thursday, then my student will have a test ready for everybody. Okay? Is everybody able to address how the first 6 questions in the homework? Good? All right, this is a quiz, right? I'll get these graded. I got everything? All right.
You want our homeworks now?
Sounds good. Let's do that.
How long will you be gone?
I will be gone until Thursday. I will be back on Friday. I'll be basically out most of early of the week. Mm-hmm.
Do we need to turn the second homework in? Or is that just for
Yeah,
the review on?
please send me electronic, so I do want to grade it while you are away. So give you guys some feedback, okay? Mm-hmm. So how's the generally for this new chapter compare with the last chapter for you guys? Much easier. I'm surprised. Really? Okay. So I expect you guys, everybody, score a 90 percentile up, because last one it was like 84, 85.
See, Sam, you set expectations way too high.
But I do. It's slightly more abstract in terms of understanding why they phase separate and what's the driving force, right? So what I want to say a few expectations before I start a lecture for this part is, first I will talk about, I feel for this particular lecture or chapter, what you guys need to learn or take home message is you guys have to understand why polymer phase separates, what's the driving force, what you could do to promote its mixing or non-mixing, okay? Those are key conceptual concepts you have to master to do well in the test. Yes, so the key, this particular chapter, which I will talk in the end, just to recapture what I just said, is going to be tell you guys all about what is the phase diagram of the polymer and what it promotes the polymer to phase mix, what is not, and what is individual contribution to it. Okay, so you guys should know.
I have a question.
Please.
Is the, like, if we consider this structure, it's basically of the thermodynamic perspective to, like, if the polymer solution or like mixture polymer will separate or not, is that the thermodynamics only the reason gonna like control it?
Of course not. So it's very easy to understand. Why? Because there's always an argument that kinetics will play a role. So what do I mean by kinetics going to play a role? I can give you an example that in very cold winter in northern part of the U.S., you would have water become ice, start dripping down. You fall these long ice chunks. They're not going to be fall down before you give the system enough energy. So same argument for the phase separation. Thanks, Sonia. You need to have the system to have enough mobility to make it happen, okay? Mobility, I mean, you cannot freeze the polymer chain when you mix them. That's something called the kinetic traps states, and it's quite common in some of the materials. Like Sergey will teach you guys about glass transition temperature, which I won't steal his thunder. He will teach you all about the science related to the glass transition phenomenon. But in a short sense, glass transition temperature tell you what is the temperature at which your polymer chain start to have mobility. Let's say polystyrene is 100 degrees Celsius. And if you have second material is also glassy, which may be polyethylene, is also somewhere about 70 to 80. Then if you mix them in the melt, in the high temperature in the one phase region, let's assume you can reach that. So it will fully mix. If you slowly cool down, it will fast separate. If you kind of think about the USTC phase diagram, right? In high temperature, it will one phase. In low temperature, it will be two phase. If you cool it down slowly, they will phase separate. But if you quench it, specifically, I mean, you lower the temperature so fast that phase separation haven't able to happen within the time frame given to it, then you would have frozen states in terms of two polymer intermixed at room temperature. It is not the lowest energy state, because if you heat it up, it will phase separate, or if you give something mobility to the polymer, it will continue to phase separate until reaches lowest thermodynamic states. But because the kinetics play a role, you do not allow the system to relax to their states, so you wouldn't have totally phase separate.
So when we like come to a real cases, some conclusion we draw from the thermodynamic perspective is not very valid?
So I wouldn't say that. This will tell you what's the long-term performance for your material or long-term thermostable states, but not a lot of. We do need to consider the driving force, because if you think about engineering and plastics, if the chi parameter is high with time, you start to phase separate and lose performance. I actually has a very great example for the field I'm working in called a polymer solar cell, where you mix two materials together, and the key driving force for the device to have a good performance is you want the material to be intimately mixed. So on the phase separation about 10 nanometer, which is very small in terms of phase separation. In any phase separate states, it will go above micron scale. So what we use to create those intermixed states is basically dissolving in a solvent. So both A and B are dissolved in a common solvent at low concentration. Then we sprinkle them, that solvent evaporates very fast. So this quenches your two polymers into intermixed states. It's created a beautiful device. It has record high performance. Nowadays, it's even competing with inorganic silicons. But one of the caveat people find that is your two-phase, if you do not engineer their chi parameter properly, because if you still have a driving force, a high chi, your material will phase separate in the elevated temperature. So if you put the solar cell use the outside, your surface can be as hot as like 80, 90 degrees. Don't touch a black object in the summertime because it will burn you, right? It will start phase separate. So one way people are trying to address is really now at the molecular level you want designed so that they have low chi between two phases. So when you cast them, they were trapped, but because the chi is low, you don't have a lot of driving force for them to phase separate in later on, or even they would prefer in the mixed state, no matter what temperature range you are at. Okay. So that's a very good question about if the phase separate will be kinetic dependent. Okay. So I want to have a recap before we start talking about today's class. The last class was kind of heavy in terms of talking about phase diagram, if your material will phase separate or not, and we discussed the concept about spinodal line and binodal line. And some of you had some question, and we chatted about, explain about the concept and how to link the two of the figures together. One is the delta G, the free energy diagram, versus the phase diagram. How do you link two? So today's lecture, we just have left some of the concepts we talk about with regard to regular lattice theory. How do you determine spinodal line? How do you determine the binodal line? And how do you determine the critical points, right? And we have just a little bit left in last lecture. Let's continue to finish it. Here we go. So this is the last part where we now start to talk about Flory-Huggins theory, where now we start to apply when your system actually has polarly dispersity. So this would be the phase diagram for a polymer in solvent. And in this phase diagram, this plot is temperature versus volume fraction. And you can see this is only some part of the figure. It's not phi 2 is from 1 to 0 all the way to 1. This is only chopped part of it. And because this is a polymer solvents, that's what you would expect. The phase diagram will be tilted towards one side versus the other. Okay? It's not going to be symmetric. So what happens is now we have three different kind of cases where they both show UCST, but they have different molecular weight. In this particular case, we're trying to show A has the highest molecular weight, where C has lowest molecular weight. Molecular weight will play a role in the critical points. If we kind of recall in the last lecture, we talked about how does molecular weight depends on the critical points, where is given by this equation, where, as you can see, as n goes up, your critical temperature will go up as well. Okay? So how do we understand this? This basically says if your molecular weight goes up, it's less likely or much harder for your polymer to mix. So you need to increase the temperature more to create the more driving force in terms of entropy to make the system mix. That's molecular weight dependent. And similarly, we need to think about what is the polydispersity in the molecular weight dependence. And anyone would have a guess? If the molecular weight start to play a role, now what would be the polydispersity in terms of molecular weight come into play? How does polydispersity affect your phase diagram? Let's say you have monodispersed PDI equals to 1 versus PDI equals to 2. Anyone want to take a brief dive? Sonia, please.
Would it be less likely to mix with a higher PDI because there's different effects that are going to be impacting the system?
Right. So the PDI will create a rule. PDI, the higher the PDI, as you can see, will create a broader transition in terms of phase diagram. This is where you have a T versus phi. If your polymer has different contribution into the phase diagram, the low molecular weight, which is case showed in this line, which will phase separate quite differently in the high molecular weight. So you would have a basically quite an interesting system where you could have some of the material already phase separated, but some of them are still dissolved. If you want to drive everything into the two-phase, you have to lower the temperature to this point, which is related to the lowest molecular weight. Okay. And this is where the upper boundary, where your polymer will start to phase separate. And it's pretty much describe the polydispersity effect. That's pretty much summarized the phase diagram. So I'm wondering, everybody has any questions regarding the phase diagram? If not, we're going to go to the next chapter to talk about what is chi parameter.
Are you saying that phase separation occurs in this region or in this region?
Phase separate going to happen in this region inside of here. That's basically what you would expect in a typical UCST curve. How do we draw a phase diagram? Good question. I think that's pretty much says we need to visit one of the paragraph. This one more time. So in this graph, okay, listen very carefully because this is probably the most important advice I'm going to give for the chapter 7. What do you see in this graph?
The points that the equation solved for.
Yes, the 5-point equation solved for, which is related to. We actually see several ways of have different line. We have a solid line, which is basically show here. 1, 2, 3. Can anyone guess what those 3 lines would relate to?
The delta S, delta H.
Delta S, delta H. And it's related to delta G, right? It's basically the delta G at various different temperature. Okay, so I'll give you an example. So more specific, this would be the room temperature. This would be 50 degrees Celsius. This would be 100 Celsius. Just to help you guys understand, at different temperature, you would have 3 different lines into delta G divided by RT. That is pretty much determined by the entropy and enthalpy equation given by the Flory-Huggins theory, right? So you have delta G going to be equals to delta H minus T delta S. And at changing delta T, you would have different value of that. And we can be more specific in the Flory-Huggins theory. Let's say for the polymer, that's why your delta G will be a function of the phi. And that's how we get those 1, 2, 3 curve shows up. And please pay very important attention. The delta, this is plotting delta G. And the question back to you, how do we get the phase diagram? We basically get from the delta G curve. At each temperature, you would have a data point at A, B, C, D, E. A and E binodal. How about B and D? Spinodal. And you have critical points which should not shift with. So now at a different temperature, at 50 degree, again you would have the same A, B, C, D, E right here. But the position will be shifted, right? Robbie, right? So if you keep changing the temperature, at some point your delta G will not show anywhere you have unstable state. It's always going to be concaved up, because when temperature is high enough, your delta G will always go down. There's different fraction. That means you're reaching at the state that you're always going to have mixed state, right? So if we repeat this to not 3 data points, we only have 3, right? So if we only have 3 data points, what I can do is now tell you 25 degree, I know I have points A will be, what is this? What happens in 25 degree in point A? That's going to be spinodal. Oh, but let me see, binodal, right? A is at binodal point, correct? I know where the B is. I know the C is. And I know where the D is. And I can get a E. 25 degree. If A, I can look it up what is phi A1. So now, how about temperature at 50 degrees C? Again, I can repeat it, but let's call it A prime. Going to be here, right? A prime will be somewhere between A and B points, right there. And you're going to have a B prime, C, D prime, and E prime. Probably somewhere there. Okay? And we're going to have one more temperature, 100 degrees. We know we have basically one critical point right about here. So if we repeat the same process for many, many times with different temperature, what you would get now is a smooth line for all the A points, and they would follow this line, A and E, which is basically this dash. So, just one sec. So this is how we get phase diagram, because now this dashed line is basically the phase diagram where we have showed in the other class, where you now can look up, this is going to be 2-phase metastable phase and 1 phase. And that's how we connect the 2 worlds together through a warm tunnel. Everybody following? Okay? Make sure you understand what's the linkage between these two. Sonia, you have a question? Sorry?
Yeah, is this for polymer solvent only, or is it generic?
It's generic. So this then depends on whatever your structural polymer. This applies to the lattice series as well as Flory-Huggins series. The only difference is just how the shape of your curve will be look like. In the Flory-Huggins series, your phase diagram will not be symmetric. Symmetric specific, I mean, the highest point will be at 0.5, right? Because the entropy contribution from polymer chain is smaller, so it will be distorted in one way. Pretty much like this phase diagram. You can see? It's more, if I would have something in the center, I would pull the critical point to the left. That's pretty much what gives you the polymer phase diagram. But if in the case of polymer, if your degree of polymerization is the same, you will end up again a symmetric phase diagram one more time, okay? So let's pretty much summarize this part. So in today's lecture, we're going to discuss about what is the Flory-Huggins parameter. We have talked about way back at the beginning of the lecture, we discussed Flory-Huggins parameter in terms of polymer-polymer interaction. Anybody remember the lab notebook? Lab notes? What does chi coming from? Where does chi come from? Anybody remember? We basically defined the chi value based on the delta W value, right? So we defined chi will be basically relate to, let me make sure I got everything written down correctly. Chi will be equals to V1 RT and divide by Z divided by 2 W1 2 and this W1 2 is interaction between your solvents A versus the B in assuming it's a lattice theory. Remember, we have made a lattice where we define what is interaction between different color of the lattice, right? If you have the two of the empty ball interacting with each other, we define this is the interaction force W11. If you have two, let's assume this is a solid white ball, you have W22. And that's where we define the chi parameter. So we also learned throughout the course from the osmotic pressure, chi and the B has something to do with the interaction parameter between different solvents. When in the theta solvent condition, I think everybody should get this for today's quiz. This will be 0.5 and B2 will be 0. So clearly chi is a parameter will tell you physically relate to some sort of polymer interaction. And today's lecture is about what is this. Somebody help me, describe me what is chi? Anyone? It is sort of well described in the book. In the 7.7 talks about chi parameter. It is interaction parameter. And let's think about fundamentally what is the interaction parameter you had between two different molecules when they're relatively close to each other. Let's say I'm here closer to Sonia. What kind of interaction? Think about nanoscale.
Attractive versus repulsive.
Yeah. What contributing to attractive? What contributing to the repulsive?
Gluon exchange. Gluon exchange.
What is that?
Gluon exchange? Isn't that what the attraction is of the quantum model?
Classically, we usually describe them as Lennard-Jones interaction. Lennard-Jones describe what is interaction force you have versus displacement, okay? So we can kind of generically know if this is going to be interaction defined by interaction energy, this will be the distance. Assume this will be packing distance between your two different molecules. Average, it will follow this way, okay? And it will plateau. So in this direction, because it surpassed the equilibrium distance at R star, your polymer will have more repulsive force. You can think about this would be the comfort zone or personal zone a molecule would like to have. If you enter that zone, there's going to be a lot of repulsive force between each other. Well, on the other hand, if they are a little bit far away, then this is coming from dipole-dipole interaction. So can someone tell me what is dipole moment means? Partial charge. Okay, that's one answer. Surabi, what do you think?
Charge multiplied by distance.
So it's related to polarizability of your molecular. Polarizability specifically talks about if your polymer is in an electrical field, how much you can induce a dipole moment, or induce a negative charge versus a positive charge on the other hand. We can generically say two interaction parameter Wij will be proportional to polarization ability or dipole polarizability in terms of R, Ij, distance, power of 6. So what are these three parameters? We define alpha is polarizability, or how easily your material can be polarized. This on the bottom, Rij, is a distance between two components. Specific mean if I have one here, one solvent molecule in one of my hands, if the Wij or polarizability is no, then it will depend on the distance, how much force they would have. If they're very close, they're going to have stronger attraction force. While they're pulled away, then the attraction force will drop over time. Okay? And this polarizability can be used directly to understand how much force you need to pull two of the molecule apart. So as you can see here, W11 will be exactly related to alpha 1. Alpha 1, same molecular, and the molecular distance Rij, power of 6. As you can see, this force decays very rapidly with the distance. If your distance goes up, it drops almost like dramatically to the bottom of the floor. That also tells you if you have two totally moleculars away from each other, there's not much interaction force between these two. There's just going to be no force at all. Okay? So how does this relate to the chi parameter? That's a question we're actually going to address today. The polarizability is an intrinsic parameter can be measured for a given polymer or any molecular or any material. Okay? Some of the molecular has easier polarizability than the other, which should be very easy to measure. Well, if we actually know what is interaction between 1,1 and 2,2, we can infer the interaction between 1, 2. Specific might mean W11 would be proportional to, there's a minus sign right there, minus alpha 1, right? That's the interaction, potential interaction force from molecular, let's say A. And you would have molecular B now this is a little bit tricky, but in the lattice theory we basically say the distance from AA, distance from BB, and distance from AB will be all the same. So in other words, we assume R11 will be equals to R22 will be equals to R12. Right? This is something you can do in a ladder series. And the goal we're doing this is now trying to come up with a scheme that as long as we can measure what is polarizability, we can give, we can actually tell you what it would be the chi parameter. And this is important because if you can look up a polarizability, or later on we will define the term, we can look at a table and figure out what the chi value between two molecules. That is quite amazing, because measuring chi directly between two materials is not straightforward, as you can tell. But if there's a handbook or somewhere I can go and look it up, what is chi parameter, then my formulation job will be easy. I'll just look at the polymer handbook and check which material or solvent is closer to polystyrene. Then I compatibilize with polystyrene, right? So this is quite practically important for this part. How about one more term? W12. W12 will be equals to minus R12 power of 6, alpha 1, alpha 2, right? One of the beauty about this interaction force is now we can sort of link what is W12 to W11 and W22. They are somehow related. And we can basically reach out a conclusion that if R11, 22, and R12 is the same, we can rewrite this to be two parts. We can rewrite this to be R12 power of 3, alpha 1, multiplied by alpha 2, R12 power of 3. This should be exactly the same. Nothing changed. This will be root of W11 multiplied by root of W22, or you can get the interaction parameter in terms of W12 will be equal to the root square of average of 11 and 22. Okay? Now, we can further simplify one more physical term is on the top here. This now chi can be simplified as well, as long as we apply, I'm pointing in the wrong direction. This is going to be W12. This, if you do this, apply this W1122 to replace W12, you can immediately get what is chi will be equal to minus and multiplied by n a z to vi. Okay. And it will be need to minus NA Z to VI. Or we can define a new term called cohesive energy density. So this new term, short for CED, would be equals to minus cohesive energy density, CED. Let's slow down a bit and explain what is cohesive energy density. So we basically define that Wii will be equals to this delta I square. Okay? Cohesive energy square is basically directly proportional to Wi, or interaction parameter. And this the physical parameter is being reported in all kind of polymer handbook. Let's say if you buy a polymer handbook in the 90s, 80s, you turn to the physical property, you can look at cohesive energy density. Cohesive energy density is basically tell you how much you would pull two molecules further apart and what the value would be. Similar to the Wii. Well, there's one more step we need to talk about. So, if you know that the cohesive energy density can be defined, then your chi can be replaced using this term. Your chi will be strictly square. Okay? So those are cohesive energy density for this is for B. So two type of different solvents. RT is no. VI is molar volume for your molecular. So chi can be simplified to be just relate to the cohesive energy of a molecular. To be more exact, if chi cannot describe one material, if you have only polystyrene, you cannot say chi for the polystyrene something, because chi is related to the interaction parameter with second molecular. Let's say you have toluene and the hexane. So how can we get the chi for these two? Well, cohesive energy gives you a simple way you can get the chi value. You can look up cohesive energy. Cohesive energy doesn't depend on two molecular. It is only determined by itself. Cohesive energy tells you what is the energy to pull, let's say in the toluene solvents. You have millions of toluene molecules sitting in this room. What would be the energy we ask one toluene molecule to be vaporized? That would be the cohesive energy. Okay? That's very much related to the W11, as you can see. Cohesive energy squared is proportional to W11. And this is a parameter that don't depend on a second molecule or a pair. Because I only need to consider what's the interaction within toluene. If I remove one of the toluene molecule, you can calculate it out. This is something you can directly look it up. Now let's think about one scenario, how we can use it. You know what's the interaction need to move away one toluene all the way to infinity from this room. We also know what is the energy need to remove a hexane. Now you can calculate chi parameter based on what we have discussed. If you know the cohesive energy density for one, and you know cohesive energy for the second material, it will be the cohesive energy difference square. That will give you the chi. It is so simple. So if you want to create a low chi combination between two materials, what would you do? I give you a polymer handbook. I ask you which material I can compatibilize with polystyrene. All right, that's your day one in the engineering job. Your boss is very excited you're on board. He gives you the most exciting project for the company. They're making a next generation plastic composite for Tesla. I ask you, how can you make it compatible with polystyrene? What would you do? You need to tell him, you first need to buy me a polymer handbook, cost about $1,000. Then I'll look up cohesive energy for you, and you can track down the list and start looking on what molecular shows similar cohesive energy. And there's actually an old saying for this finding. They call it likes, like. So if you have polymers show similar cohesive energy, they actually will like each other. If you have two polymers shows very different cohesive energy, they will not mix with each other well. Okay? So it sounds like it solved all the problem. Please? Well?
I was going to ask, so what if you're making a novel polymer and you don't have the cohesive energy density? Can you like use instrumentation to find that? Or how did you originally solve for that?
Yeah, you can certainly look for that. Cohesive energy can be measured. It need to measure what's the enthalpy to vaporize your material. Because if you think about what's the definition at the beginning of class, we need to consider how much enthalpy participating moving molecular parts. So a direct way to see that is basically vaporizing all the solvents. Okay? How much energy you need to vaporize. But it turns out to be your engineer and manager is still going to be mad at you because this simple equation doesn't describe all. It is oversimplified. And I want to emphasize it's empirically you can crack that, and it's only for empirical reason. Empirical relationship tell you your chi is always going to be a little bit underestimate. So chi effective will be exactly the same equation I gave. Plus 0.34. And 0.34 is sort of an empirical term. People don't know why. It just works out. If you do sample all the different molecules, they will actually closer to what your finding is. It's not going to be exactly the same. This is not going to be, even this equation, empirical, it's still going to be exactly what you're going to have, but it's a good starting point. You can tell your manager, I narrowed down those 5 polymers. I'm pretty sure those are the good starting point. You know, still quite useful in that sense. Why? Why this sometimes fails? The deviation is actually comes from one key parameter we never talked about is what if your molecular has additional interaction? What is not just a dipole-dipole interaction? If we in this particular case, we only assume that the W12 is related to the dipole-dipole interaction with polarizability of alpha versus distance. If your molecular has additional parameter, let's say if we form hydrogen bonding, if you have other type of electrical charge, then your chi parameter will be changed accordingly because you have additional interaction between two phases. If that is involved, it's actually rather complicated to describe in a few sentences. So this is still a field that has a lot of research people are trying to address. But for a starting point, if you just go out, you just want to make some simple calculation. The chi parameter based on cohesive energy density give you a good starting point. Okay?
I have questions.
please.
We get the cohesive energy density and we like refer back as like solubility parameters and that describe like the single type of molecules. When we only talk about this one type of molecules, those like interactions should be like included inside.
So for one material with itself, usually it's already considered because when we talk about solubility parameter square or cohesive energy density, it is considered there.
Yeah.
Okay?
Let's say if this molecule has sort of like hydrogen bond.
So hydrogen bond, then you need to consider another parameter, which is also an empirical equation called the Hansen solubility parameter, where you can consider what is a hydrogen bonding contribution in terms of solubility parameter.
Yeah.
I can refer you some of the journal article. You can take a look.
Oh, like my question is just want to ask, are those interactions included in the W2, W11 or W22?
No, it's not. That's why, based on simply calculation using a cohesive energy square, the chi you get could be off quite a lot.
But it was like W11, W22 was like directly related to the vaporizing function.
Yeah, that's right.
And vaporizing is a like physical process, which is affected by like multiple interactions. Like
Yeah. So that is the case, as I mentioned, solubility parameter or cohesive energy density. When you measure those, they are considering all kind of possible interaction.
correct.
But let's say the molecule AA, and when we consider BB, then consider AB in terms of AB phase, we did a lot of really oversimplified assumption. One of them is we assume that molecular size is always the same or lattice size is the same. So R11, R22, and R12 is the same. But it could be different, right? That's one of the variable we didn't really come into full consideration. The second is when you consider the interaction parameter. If you have 1, 1, 2, 2, then 1, 2 could introduce some new interaction force. Let's say if your polymer 1 or solvent 1 is always positive charged, B is always negative charged. So 1, 1, 2, 2 is going to be always a repulsive force. But once you mix them, it's going to become some more attraction force. So in a nutshell, I don't want to say using the empirical equation will be perfect, but it's something that you can convince your manager in your future job it's a good starting point. We can narrow the 1,000 candidate maybe to 10, and then you need to do more work to figure out among the 10 which is best. Yeah. Say that again.
How do you find excluded volume? That's V, right?
Excluded volume, is in the solvent when we talk about good solvent, bad solvent. Is there a particular reason you ask? Good solvent?
Oh, molar volume, sorry.
Oh, molar volume.
Yeah, that was my mistake.
Molar volume is basically defined by molecular weight divided by the volume.
Okay.
So how much your 1 mole of your solvent occupy how much your volume.
Okay, thank you.
So if you know the density, you know the molecular weight, you can calculate what is molar volume. Okay? So it's sort of
Is that what V1 here is?
yeah, V1 is molar volume. Those are usually just constant, but really changes your chi parameter effective is solubility parameter or this delta 1 is solubility parameter or cohesive energy density, which is square of solubility parameter. So at the end of the day, when I look at the phase diagram, if polymer solvent, what I really need to do is basically have a polymer handbook in hand. I need to know what the chi parameter. Then I can eyeball what will be the entropy contribution, and this will be the enthalpy contribution, right? And as we mentioned, chi is always going to be larger than 0. because these two terms are always going to be positive. Solubility parameter 1, 2 squared. But chi equals to 0.5 is an interesting value. 0.5 is where you have zeta solvent. Okay, I want everybody to understand that. And when the chi goes up, that means there's more unfavorable interaction. And that's counted by solubility parameter different. If your chi is very large, that means your solvent, your two materials are less likely going to mix. Okay, so last part we can just chat a little bit about what is solvent quality. And we sort of already talked about in the first lecture in terms of chain conformation. So we're just going to briefly recap. Remember the scaling law, how does molecular weight, Rg depends on the molecular weight. In the good solvents, Rg will depends on molecular weight power of 0.6. That comes from the excluded volume effect. And in the zeta solvent, Rg will depends on molecular weight power of 0.5. And that's we also studied. That's the ideal chain. Okay. And we also know the collapsed globular, you would have Rg power of n power of 1/3. That's related to the diameter of your sample. So in the textbook, there is a short discussion about how you can consider the chain dimension in good solvents. So how can we quickly, using some simple ways to understand why in the good solvent Rg depends on n power of 3/3, or more accurately 0.589, sorry. So what causes the molecule to expand and what is hold back? This will help you to read that particular chapter about good solvents in 7.7. So what causes the molecule to expand? The interaction with itself, so it will have self-repulsive force, right? So you can also consider as osmotic pressure in terms of inside the individual solvent chain. So if you consider one chain coming from one large sphere, so inside this sphere you have polymer chains. You can consider what would be the osmotic pressure inside this particular globular. The osmotic pressure will drive the solvent into this globular because you have polymer chain, and outside you have pure solvent. So chemical potential will drive your solvent into this particular imaginary sphere. You would cause the chain to expand. What is the cost for the chain to expand?
Energy.
You would lose entropy. Remember, we talked about one parameter in the class is what is possible chain conformation depends on different end-to-end distance. Everybody recall that? The Gaussian distribution in terms of chain ends. You can use that to calculate the entropy of the chain, because entropy is directly proportional to possible ways your chain could configure. So now you have two competing forces. One wants the chain to expand, osmotic pressure, but on the other hand, the entropy wants the chain to relax back towards the most possible state, which is a free joint chain. So at the balance, when these two forces cancels out, that's where you have the chain size in good solvents. Okay, I'm not going to go into too much detail, but if you calculate the interaction between the polymer and polymer and versus the entropy loss due to the chain expansion, or you think about chain as an entropic spring, you can easily obtain that in a good solvent, your chain your RG will depend on the molecular weight power of 3/5. Okay, that is briefly discussed in the textbooks in the last chapter. So that pretty much covers all we want to talk about. Start from this chapter, thermodynamics, to the entropy, to the lattice theory, to the Flory-Huggins theory, and to the end of what we have talked about in terms of phase diagram. So I think we can probably just end it right now. We have covered everything. So for the homework, I will discuss it with you guys next week. For these, I will also send back, give back to you guys tomorrow. We'll take a look this afternoon and give some feedback, okay? For the second half of the homework, please just send to me, take a picture of it or scan it into the PDF format. I'll crack the send it back to everybody. So regarding the test format, it will be very much similar to what we had before. Some multiple choice, some conceptual questions, some numerical questions, and there will be 1 or 2 bonus questions. Any question for me in terms of this particular chapter?
Do you have any of like textbook suggestions for practice problems related to particularly osmotic pressure and Flory-Huggins theory? Any textbook in particular?
So the one we're starting is most a simple one. So I think the homework will be a good starting point.
Okay.
And if you want to try more,
You think about a polymer solution,
mm-hmm.
the size of the solvent molecules and the size of the polymers, like they are giant, like very different.
How do we understand? Phase is a so interesting topic. It's probably one of the major topics people favorite since to talk in quantum physics. Studying phase, you need to use a lot of scattering techniques. So study, for example, neutron scattering has been used a variety by a lot of group, Frank Bayes, Tim Large.
But those phases was what we can see from
Right.
like instrument thing. But
Right.
from theoretical part, it's a phase like have 2 different components.
Yeah.
And they have same for like certain component have same like chemical potential.
Yeah.
So like it's not very visualized.
So it will not. So I certainly see what your point is, but a lot of time the phase separation is predominantly studied by 2 techniques: microscopy and scattering. Microscopy, you can directly see which component is which, and when the phase separates, as I mentioned, they would create cloudiness usually in the solution of lens, and the cloud point determination is one way. And in the phase diagram, you don't necessarily need to get every data points. What typically do is exactly what I show here. They would get 25 degree, 75, 100. Then they're just going to plot out the boundary. Let's say I plot 7 data points here. Then my phase diagram will just be in this case, and people call it here. It's going to be single phase, and outside it will, inside this will be phase separated domain, and outside will be one phase. That's how people typically study the phase diagram. You don't need to go through every single data points in the phase diagram to map out the phase diagram. You can kind of imaginary extract it's going to be along the way.
Okay, I feel I'm confused about the phase pattern
Mm-hmm.
and like 2 phases itself. Like think about you have like 2 like material mix.
I think the class is over, so if you guys want to leave, let me know, and we can continue to talk about that, please. So regarding the particular question you asked, yeah, we can discuss this a bit more until you understand. Yeah.
bonus questions would be the same as divisions, like first
I,
example? Or-
so you ask the bonus question.
Yeah, like last
It
time.
will be a surprise. I cannot tell you.
A surprise, okay.
Yeah.
How many derivations are we supposed to, which kinds of derivations should we know?
All of them.
What is would be entropy, enthalpy, and Flory-Huggins theory? Something I would not go beyond textbook. So go back to check the largest. Yeah.
What is the question for?
Why is there
So one second.